Chen. Today we'll be talking about the concepts of vapor pressure, how that relates to changes of state, as well as phase diagrams. Now, we very briefly talked about vapor pressure, Dalton's law of partial pressures, when we were doing our gases chapter. We're going to be going into a little more detail in this section. We're going to be talking about enthalpy of different states of matter changes. So vaporization, sublimation, things like that. So going from a liquid to a gas, what is the energy required to make that happen? Is it endothermic? Is it exothermic? So we're going to be applying thermodynamics now to these changes of states of matter, which means we still need to be understanding what's happening with those inter-ER molecular forces for that to happen. So the first one we're going to talk about is a heat of vaporization, which is very simply just the energy required to vaporize 1 mole of a liquid at a pressure of 1 atm. So we have kind of these standardized enthalpies of vaporization, and it's just so that we can compare everything equally, so 1 mole of that material at 1 atm. Vaporization will be endothermic in nature, and sometimes this is hard for people to understand, but think about it. To go from a liquid to a gas, we have to add heat, right? Think of boiling water, liquid water, and turning it into steam. You put it on the stove to do that. So you're adding heat to the system. So this would be endothermic. So we want to think about what happens to a liquid in a closed container. So there's going to be this constant exchange going on from the gaseous state to the liquid state. It just naturally occurs. But what ends up happening is if we pour, in this case we have water, let's just say, into this flask, over time some of that liquid water will escape into the gaseous phase. Now it can't go anywhere because we've capped off the top of it. So those gases will kind of hang out, and eventually we'll reach a point at which there's gases escaping into the liquid phase at the same time that gases escaping from the liquid phase to a gaseous state, and then gases or vapor, right, that will condense and come back to the liquid state. So this will be happening at an equal rate. And we call this equal rate equilibrium. And basically, it's no further net change occurs in the amount of liquid or vapor that is present in a closed container. So we will have a constant changeover of which molecules exist in the gas and which molecules exist as the liquid, but there's no overall net change, or the total change will always have, I'm just going to make up a number right now, 10 molecules existing as the vapor and 10 molecules existing as the liquid, or 10,000 molecules existing as the liquid. Now, which one of those molecules is liquid and which ones are the vapor, that will change, but the overall, whenever we take a snapshot at a molecular level of that compound, of that material in that container, we'll always have that amount of each liquid and vapor. So the rate of condensation is going from gas to liquid, equals the rate of evaporation, right? The rate at which we're going from liquid to gas. So they're equal rates. What ends up happening is that vapor pressure is the pressure of the gas at equilibrium. So here's just kind of a visualization of that, right? If we have our rate of condensation, right, the rate at which it would evaporate is constant. But the rate of condensation, the more gas is present, the more likely it is to condense. So that's why this curves and increases over time, and eventually will reach an equilibrium where the rate of the evaporation is the same as the rate of the condensation. So how do we measure this? A measurement of vapor pressure can be something as simple as a barometer. Sometimes if you have a weather app or something like that, we'll have the barometric pressure, and that's the pressure in the atmosphere, typically of like the water vapor in the atmosphere. And so obviously this last week we had a lot of rain, so that would be affecting our barometric pressure. In terms of what we're going to be looking at, sometimes we use things like column filled with mercury that sits in a bowl that is exposed to the atmosphere, and how high or low that mercury rises that we measure in millimeters will give us the pressure of the vapor in the air. And this is where we get the unit of measurement, millimeters of mercury. So if you see mmHg as like a pressure reading, that's literally coming from this type of system setup where we have mercury in a tube, and the changes in the mercury as it rises or falls is measured in millimeters. So the vapor pressure, right, just kind of like how we experienced before, vapor pressure in the atmosphere is going to be the pressure of the atmosphere minus the change in pressure that we see from the column. So here's a kind of an example of that, right? So we have a dish of mercury, and this is open to the air, and this is the column of mercury filled. And then we can measure if the mercury goes up or the mercury goes down. So this is just the vapor pressure in a vacuum, right? So 760 torr is the same as 1 atmosphere. And then if we had water vapor in here, right, the vapor of the water is going to push down on our mercury and push some of it out. And so we still have the atmospheric pressure, which is the 760 torr, minus the millimeters of mercury that we have from the water vapor pushing down on it. So we get a vapor pressure of water at 24 torr. Here we have ethanol, and then we see that that has a greater vapor pressure, and that we get 70 or 65 torr. And lastly, we have ether over here, and this has a very big vapor pressure, right? Look how much of the mercury it pushed down, so much so that we have 545 torr for this. I would encourage you to pause the video here, go ahead and draw out the Lewis structure of each of these materials. Look at the types of inter-ER molecular forces that act on each of these. Determine who's going to have the highest boiling point, who would have the lowest boiling point, and how that would relate to these vapor pressures that we're seeing. So here's your second door question for Chapter 10. So liquids with high vapor pressures are what we call volatile, which means that evaporation occurs rapidly in just a regular open environment. So if you've ever experienced maybe pouring or accidentally spilling like a glass of water and then accidentally spilling like nail polish remover, if both were just to lay out on the counter and you didn't wipe them up, which one do you think would evaporate first? Hopefully you think the nail polish remover would evaporate first, and that's because the nail polish remover is more volatile than the water. The size and strength of the intermolecular forces in that liquid will determine this vapor pressure. So think about it. If we have a liquid that has a lot of very strong like hydrogen bonding inter-ER molecular forces, then it's going to want to hold on to that water molecule right next to it much, much longer. So it would take a lot more energy for it to break apart into the gaseous phase. So the stronger and more molecular forces, intermolecular forces we have, the lower the vapor pressure would be because less of it would want to escape into the gas. And we can do the same thing if we're talking about nonpolar compounds, right? If we don't have dipole-dipole, we don't have hydrogen bonding, then we only have London dispersion forces, which means then we're just looking at the size of the molecule, right? So the size of the molecule will dictate how many intermolecular forces there are. So a bigger compound with more more London dispersion forces will have a lower vapor pressure than something that is smaller. And then obviously vapor pressure is temperature dependent. So think about that, right? If we add heat to a system, then more of those molecules could escape into the gaseous form. So we'd have a higher vapor pressure. So we can actually plot vapor pressure versus temperature. If this looks kind of familiar to what you did in lab experiment 2, that's because this is, we used it just to graph straight lines, but this is a way for us to start applying that. So this is how we calculate and kind of use our information to determine either the vapor pressure or the enthalpy of the vaporization or the temperature at which that energy would occur based off of a straight line. So obviously, because it's a straight line, that means it forms the y equals mx plus b type of equation. So this is breaking down all those different factors into their y, x, m, or b equivalent. Okay, so let's say these were different compounds, diethyl ether, water, and ethanol, which these relate to the colors that we have here: water, ethanol, diethyl ether. Same colors, same ones here. So just so that you can relate them, okay? Using the plots in the figure, determine whether water or diethyl ether has a larger enthalpy of vaporization. So now we have to relate that equation to these slopes. So to do this, we have to look at the natural log of the pressure of vaporization, right? So that's our vapor pressure, is plotted as 1 over the temperature, and the slope would be that enthalpy of vaporization. That's what we're trying to figure out, which is going to be bigger. So we have to look at the slopes of these lines. So when we look at the slopes of these lines, which is more drastic? Is the slope of water more drastic, right, or the diethyl ether? Because they're both negative, right? We understand because of this negative sign right here that they're both going to go in the negative direction. But the line for ether has a smaller slope. It's less drastic, which means that R is a constant, so the only thing that's affecting the slope is this heat of vaporization, that we're going to say that the ether has a smaller delta H of vaporization. And this makes sense. If you draw the Lewis structure of ether, we see that it has no hydrogen bonding, but water does. So it's going to take more energy to break apart water into its gaseous phase than it will for the ether. So this all comes together in what we call the Clausius-Clapeyron equation. And what we can do is, when we know the value for the heat of vaporization and the pressure at the vapor pressure at one temperature, we can use that information to calculate the vapor pressure at a different temperature for that same system or that same material. This assumes that this C, this constant, does not depend on temperature, right? So we can use it to determine a new temperature. So we can rearrange our equation to kind of give us this general formula. So if we knew our heat of vaporization and we knew one of these vapor pressures at a specific temperature, we would be able to determine the vapor pressure at a new temperature. And again, please keep in mind that your temperature should be in Kelvin for all of this. That way we don't have any discrepancies arise from like a negative value for a temperature. So you can go through and utilize the Clausius-Clapeyron equation to solve for this new vapor pressure. So we're told that the vapor pressure of water at 25 degrees is this pressure, and that the heat of vaporization of water at 25 degrees is this. So calculate the new vapor pressure of the water at 50 degrees Celsius. So the first thing you want to do is go through and identify what each of your factors are and where they would go into our equation. So we can see here that what we're solving for is our second, or our new, vapor pressure at this higher temperature. Remember that we have to go from Celsius to Kelvin. So here's our 25 degrees Celsius, here's our 50 degrees Celsius, now written as Kelvin. So we can go ahead and solve for our second vapor pressure. It's very, very important here that you go through these steps on your calculator and make sure that you're getting this number. If you do need help using your calculator, it's important that you let me know ahead of time so that we can set up some office hours to get you on the right track, because everyone's calculator is a little different, and I want to make sure that you all know how to use your calculators. The next thing I want to talk about is the concept of sublimation. It's a process in which a solid goes straight to a gas without going through the liquid stage. The most common one that people probably are aware of is when we have dry ice. So if you go to the grocery store, or if you've ever packed meat or something like that to travel for long distances, oftentimes it's put on dry ice. Dry ice is a solid obviously like kind of comes out like a brick, and it's white. Sometimes it's like little pellets, and it's very, very, very cold, and it's super cold and super cooled down CO2 gas. And what we do is, at room temperature, it's so hot that it goes straight to the gaseous form without ever experiencing the liquid form of it. So we can look at these changes in state, right? These going from solid to liquid to gas, or solid to gas, or liquid to solid. These different changes of states of matter by looking at what we call a heating curve. And this plots temperature versus time, where energy is added at a constant rate. So again, remember, for the purposes of what we talk about, energy is a form of heat is a form of energy. So when a solid is heated, right, it would melt to form a liquid, and then if we continued to heat that, we would eventually reach the gaseous or the vapor stage. The other different type of enthalpy that we're going to talk about is an enthalpy of fusion. So we talked about an enthalpy of vaporization already, but we also have an enthalpy of fusion, and this would be going from the melting point of a solid. So fusion, right, is going to be what we go, vaporization was when we went from the liquid to the gas. Fusion is going to be the reverse, right? We're going to go towards the liquid and solid. So here again is kind of like a description of a heating curve. This is with H2O going through all its different states of matter. One of the important things to remember here is the horizontal lines are where we're having a change in state, and that the vertical or more vertical lines that have slopes, these are where it exists in one state of matter, just going through different temperatures, right? So we know that ice melts at 0, so from 0 to negative, in this case 20, it's all ice. It could be slightly warmer ice or really, really cold ice. It's just ice. And you've probably experienced all different temperatures of liquid water, right? We could have very, very cold water, we could have very, very hot water, but it would still just be water. But when that water reaches that critical temperature in either of these directions, we will see a phase change occur, and no temperature occurs. No temperature change occurs with that. It's just a state of matter change, and then once it reaches that state of matter change, then the temperature would start rising again. So here are different melting points again, and their fusions, enthalpies of fusions, and we're going to talk about these and how we would solve for this, but I just want you to look at these in terms of seeing the trend with the compounds that we have going on here. So covalent, nonpolar, and then we start getting to things that are covalent and polar, to ionic, to drastically ionic and bigger. So we start seeing these trends occur. And so we need to look at melting points to be able to do that, right? And a melting point is the temperature at which a solid becomes a liquid, right? And when that happens, the melting point, the vapor pressure of the solid and liquid would be identical. So that's what we're representing here. So temperature and vapor pressure, right? The temperature at which the vapor pressure of a solid is greater than the liquid, the solid is releasing vapor, right? Which sounds a little weird, but it's attempting to achieve that equilibrium, right? We know that equilibrium means that the rate at which we're going from the solid to the liquid, or solid to the vapor, is the same as the vapor to the solid. And the liquid will attempt to achieve this by absorbing some of that vapor. Or condensing it, right? So the net effect is the conversion of the solid to the liquid through the vapor change phase, which would be a melting point. The temperature at which the vapor pressure of the solid is less than the liquid, right? So if we have the vapor pressure of the solid is less than the vapor pressure of the liquid will disappear, right? Because we're going to try and reach that equilibrium again. So to achieve that equilibrium, the temperature has to be below the melting point of the ice. In this case, we're talking about water, but in any liquid. If the temperature of the vapor pressure and the solid are identical, then they can coexist at equilibrium, and this would be the normal melting point. So temperature at which the vapor pressure of the solid and the liquid states are identical at 1 atmosphere. This is just what we would consider normal melting point of something. So we can apply this to things like the boiling point as well. Again, this would be where the temperature of the vapor pressure of the liquid is at 1 atmosphere, right? Change of state does not always occur at the melting point or the boiling point. And so we can kind of start seeing that if the factors around our system are manipulated, we don't always hit our quote-unquote normal boiling point or our normal melting point. We can have things that are super cooled or super heated where we start having these differences occur between their normal boiling point and their melting points. So go ahead and try and come up with a reasonable answer for this question. All right. So we're going to move on to the concept of a phase diagram. Phase diagrams are not something you will draw. They will be provided to you, but you will have to be able to describe them and read them to be able to give information based off of them. So there are a couple important aspects of a phase diagram that we need to talk about. So this is all for one material. So if this were water, for example, what we're looking at is the temperatures and pressures at which the solid ice exists, the temperatures and pressures that the liquid exists at, and the temperatures and pressures that the gases exist at. So we can see that temperature and pressure, right, kind of determine how close those molecules are going to have to be next to each other, how much energy they have versus how much compression they have towards each other. A couple points that we want to call out. So we have the normal melting point, we have the triple point, we have the normal boiling point, we have the critical temperature, and we have the critical pressure up here. So we're going to talk about these different points. So triple point is the temperature at which all three phases exist simultaneously. So right at this sweet spot right here, technically all three phases exist. Now remember, this isn't something that in our day-to-day lives that we see happening to the naked eye, because we're not under these conditions that we can control those things, the pressure and temperature, so exactly like that. So watching an ice cube melt, we're not going to observe all three of those stages existing at one time, most likely. A critical point is defined by the critical pressure and temperature. So critical point has two kind of pieces to it. The critical pressure, which is the pressure required to produce liquefaction at the critical temperature. So that's why those two are related to each other. When you look at it, these are on the same line here. The critical temperature is the temperature at which the vapor cannot be liquefied. So the idea here is there comes a point where the gas is at a pressure where no matter what, it can't liquefy. So, some of the unique things about the phase diagram of water is that this slope here for water is a negative slope. For most other compounds, it will be a positive slope. So if you have an unlabeled phase diagram and you see a negative slope for the solid liquid line here, you've got a pretty good chance that you're looking at a water phase change diagram. And it describes a closed system. Okay, so we're looking at a system in which the factors are being very, very controlled. At point X, which we have here, the ice, because we're in the solid, is subjected to increased pressure. So if we had this solid and eventually we kept increasing the pressure, but the temperature remained constant, right? So the pressure gets higher and higher. Eventually, we're going to pass that solid liquid line, barrier. And again, for water, like I mentioned, this has a negative slope, so this is kind of unique to water. And this is one of those things that we see in our day-to-day lives where we know that the ice form, the solid form of our material water, is less dense than the liquid form. So we know that because ice floats in liquid water. So the solid is actually less dense than it. At the melting point, right, the liquid and solid are in dynamic equilibrium, just like we talked about with vapor, the boiling point, right, that vapor equilibrium, we can have that in the liquid state as well. When pressure is applied, right, the volume is reduced. So, some things that you might not think about, right? We already talked about this, that density of ice is very low, and this is really crucial to like ecosystems in places where it gets very cold during the winter. If a river or a lake were to freeze over, the ice flowing on top means that all the life within the lake can still survive in the liquid water below. And another example with ice that we don't really get to experience, but in places where it's cold and you have ice skating, what's actually happening is there's such a narrow blade, and the weight of the person in the blade exerts such a large amount of pressure over a small area that you're actually causing the ice to melt right under the blade, and that's what you're skating on. But then as the blade passes by, because everything around it is so cold, it will refreeze again. So one of the things you might not be aware of is when we say things like water boils at 100 degrees Celsius or freezes at 0 degrees Celsius, we're talking about 1 atmosphere when we say these things. But there are plenty of places in the world that aren't at 1 atmosphere. For example, these are just a couple places pretty much on like the western side of our country. We have New York and stuff in Wisconsin there as well. But we know that different altitudes will affect pressure, atmospheric pressure. And that when we have a variation in atmospheric pressure, that's going to affect the boiling point. So it's pretty extreme when we get to things like Mount Everest, but in terms of like Boulder, Colorado. If you've ever baked a cake before or you have cake mix in your pantry, go look at it, and sometimes the instructions will tell you how long to cook a cake at higher elevations, and it's because we have the boiling point lowers. And so if you cook the cake too long and the boiling point's lower, you're going to dry out your cake. But think about it. If I don't know why I'd be baking a cake at the top of Mount Everest, but let's say I was. That means that my atmospheric pressure is drastically higher, which means there is a lot of pressure pushing down, right? It's very, very high, which means it won't take as much heat energy to be able to allow those liquid molecules to reach the gaseous state. Whereas when we have a very, very relatively low, here, wait, where is my, we'll call this ground level, or sea level for right now, right? New York is only 10 feet above sea level, so 760 torr, that's 1 atmosphere. That's our 100 boiling point. If we go all the way to Mount Everest, we're at a very, very low, sorry, I had this backwards, a very, very low vapor pressure. It's near more than half, right? So if the pressure in the atmosphere isn't pushing down on the liquid very hard, it won't take a whole lot of energy for those liquid molecules to escape into their gaseous state. But as we get higher, right, here we go from 760 to 770, we have more pressure pushing down on our liquid, which means it's going to take more energy or more heat for those gaseous molecules to escape. Here's your third door question. One of the last things we're going to talk about, we're going to look at a phase change diagram for carbon dioxide. So as I mentioned before, here is that positive slope for the solid liquid divide. So like I said, water is a negative slope. Most other compounds will actually have a positive slope here. So carbon dioxide, what you probably most experience them in are most types of fire extinguishers. We already talked about dry ice. And under the correct assumptions, right, we can even use kinetic molecular theory to talk about this. And we have what we call the van der Waals equation. And it assumes that particles of gas um, are exerting no force on each other, right? So let's go back to our kinetic molecular theory, right? This idea that the gas molecules are perfect, that we don't care what the identity of the gas is. That way we have none of these interactions occurring. And we can use this as kind of a correction factor when we're looking at our pressures of our ideal gas versus what we actually observe in nature. And so here we can see the curves, the different curves of CO2 when we have those van der Waals corrections in place. Here is your last door question for Chapter 10. By this point, you should be working on your homework for Chapter 10, as well as in the extra help section. There are a couple of resources in terms of some worksheets that you can be looking at. I would really encourage you to be reading your textbook and asking questions and coming to office hours so that we can clarify anything you might be having questions with.